Hello and welcome to another Solana tutorial. Today we're gonna have a look at the source code of Alpenglow. Alpenglow, in case you haven't seen that video of mine, is the proposed new consensus algorithm of Solana that will hopefully come soon. And so today I just want to have a look at the implementation, because in that one video I basically just gave the introduction of what it is, but maybe we learn something by looking at the source code. And this is not gonna be a super deep dive, understand every line of code and what it does kind of a video. It's more of a broad, hey, did you know that the source code is around and that you can look at that yourself if you want? And also, let's have a look at it together and maybe we learn some interesting things. That kind of a video. I just want to have some fun. It's way too hot to be productive anyway, like whatever. And then we'll do more deep divey videos specifically tailored to Solana devs once we're closer to release of Alpenglow, because things are gonna change. For instance, the commitment levels, they're gonna be different than what we know. You know, for now we have the processed, confirmed and finalized. That will change because it's a different consensus algorithm. And even if they don't change, then finalized will come much sooner, and so the way how you need to deal with it will change. But that's stuff where I don't know the details yet, so you know, I can't talk about that yet. But what I can talk about is the implementation, or a implementation of Alpenglow, and today we're gonna just have a look at it together. What did I find? I think that was it. Yeah, I think this guy, Quentin Kniep, he's one of the researchers who invented Alpenglow, or he's a co-author of the paper, senior researcher at Answer Technology. If that guy publishes the source code, then I guess that's legit. Also, people have been telling it, like people from Solana have been telling me that, actually, did you know the source code is around? It's in this repository. So yeah, we will just trust this. It's not like we're gonna like use that code, but we're just gonna have a look at the implementation. Alpenglow, global high performance proof of stake blockchain with erasure coding. This makes me think that Alpenglow is the entire blockchain. Well, it's the consensus mechanism of the blockchain. Alpenglow, reference implementation. See, that's the reference implementation. It's not the official implementation that Answer will do or the FireDancer team will do, but it's a reference implementation by the research people. It's so fun. Like, what I imagined that happened was they released a paper basically saying Solana is unsafe. And then Answer was like, you know what, let's hire those people and let them research a better solution. And that's basically what happened. I think that's how it must have gone down. And now they push for this better protocol, Alpenglow. Yeah, anyway, a local cluster example can be run with the following command. Wow, we can even run this. Sponsor local cluster with 6 nodes. As a background, maybe you want to look at the Solana Tower BFT white paper, which, you know, long time ago Anatoly released, which is actually more complicated than Alpenglow, I think. Tower BFT is replaced with Rotor, part of this Alpenglow. So how do we do this? Do we look at source code or do we just first run it? What do we do? So first of all, check out the repo is probably a good idea. Alpenglow. Should we just download stuff from the internet and then run it? That seems safe. Damn it, I need a newer version of Cargo. It's been stabilized in the 1.8.4 release. And I'm on 1.8.3. Now let's go latest. I wonder what things I break now. So we have it installed. Rust really updated a lot. I mean, it's a newer language, so yeah, maybe. Yes, now I'm on 188. Perfect. Can I now just run this? Yeah, now I can. Look. Oh yeah, we will download a bunch of dependencies that we need to build. Oh, this is fun. And again, I have no idea what I'm even doing here. I didn't look at the source code. Let's look at this script. It's just cargo running in release. Okay. We will see what happens here. There's so much though. I wouldn't even know what to look at. Create test nodes. New Alpenglow. Okay, so that just basically spins up a few demo validators. We'll see. Let's see. Once it's done compiling, we'll see what the test comes back with. I mean, this is taking quite long. Should we just look at source code in the meantime? That's how you see that they are actual programmers. So we have the block store. That's something that was mentioned in the paper. We have a pool, we have a network. Let's see, can we find what that is? The block store. Stores raw shreds per slice, indexed by slot and slice index. stores so for reconstructed slices, indexed by slot and slice index. So it's actually fully, oh look, we are running. Look at this. So it always says fast finalized, slow finalized, slow finalized. Oh wait, but we also have, how many validators do we have? Or how many nodes do we have? Maybe it's the different nodes printing those things. Voted notar means they approve. A notary vote is a yes vote. That's working quite well, I guess. But I don't really know what's happening. So let's deconstruct that. For block 200, what do we see? Repairing block in slot 200. Reconstructing block in slot 200 with parent this, which was the previous one. So that's the block from slot 199 was this one. It's the parent of slot 200. And we reconstructed that block. We voted yes for that slot. Notarized fallback, fast finalized. I would like to get like info on which validator is saying this. Or is that all from the same one? Let's see where that comes from. Adds new certificate to the pool. Certificates are assumed to be valid. Where are we here? In the pool. Where is the pool? Consensus pool. Let's try out something else before. Create test nodes 2. It looks like I have 2 test nodes. What if I had 4 and I run this? My question is, do I get more? Yes, now I get more information or like more text, right? Because fast finalized, slow finalized. So all of them say they have a slow finalized certificate and all of them say they have a fast finalized certificate as well. So all of the 4 tell me all of the things. So yeah, it would still be like helpful, like just for me to better understand what's going on if those messages would include like the validator ID or something. Do I have that somewhere here? Voter here, at least I get IDs for who voted. Pool. Okay, what do we have in the pool? Slot states, epoch info. Okay, maybe let's look from the other side. When we create the validators, the ID gets in the validator info, those validators, and then we map those validators as epoch info. Epoch info, start port. And otherwise it's just in the epoch info. So in the epoch info I have my own ID, part of the epoch info, but the epoch info is also part of the pool. So within the pool I should be able to say epoch info, own ID. That should be the current validator's ID, and I can put that here maybe to all the messages here. So now we have hashtag the number, then maybe it's clearer. So let's run that again. Small improvements to just better understand what's happening here. That's what we want to do. Slowly understand Alpenglow. There we go. So now at least we see that those infos always, they come from different validators. Validator 0 has fast finalized. Number 1 has fast finalized. Number 3 has slow finalized. Number 0 has slow finalized, and so on. That's more readable to me, because they all do the same things. But now I know from which one it comes. Perfect. Maybe I want to put that everywhere. In the voting loop, we are in voter. This self is what? A voter. We have a validator ID. I'll take that. I would assume that the voter's validator ID is the one I'm interested here. And I'm just gonna put that everywhere. And then see what that looks like. Cool. There we go. That's what I want to see. Now I always have the numbers. No, I don't. Repairing block still doesn't have it. Where does that come from? Repairing block. It's also in voter. Self is a repair. But it has the pool. And the pool has the... No, it doesn't. Okay, whatever. Don't need to print it everywhere. Whatever. Fine. Get info. We could do the get info instead. But no, I'm fine with IDs. So in consensus, we have the message loop. Handles incoming messages on all different network interfaces. We have the standstill loop, standstill detection, and triggers recovery. Right, so that's the loop for when we're a leader. If the leader ID is not us, then we continue. Simple. Can I here have my ID again? What's the self? Self is Alpenglow. Somehow I will get my ID. Let my ID. Epoch info. Own ID. There we go. Such that I can log it everywhere again. Produce block. I mean, it's not so difficult, this thing. When do we produce a block? in the block production loop. Yeah, that makes sense. Okay. If we're ready, if we already have the parent stock, we can build on a ready parent and break this. Optimistically building on block, parent hash, parent ready. So here the parent is ready, here the parent is not ready, but we optimistically build it anyway. And because the hash for the previous slot exists already in our block store, and otherwise await the finalized slot, and if it's bigger, like if the slot advanced and the parent wasn't ready, we ignore our window for block production. Continue outer. So we go into the outer loop. A nice go-to. And otherwise, when we break out here like this, then we go to the actual block production and do the produce block. That's also interesting syntax that I've never seen before. So for the slot in first slot until is the last slot in window. So that's inclusive. That's interesting. It's probably means that it's inclusive, because if I would just write it like this, that writing I'm used to, but I would need to say -1, or I say this. Interesting. Never seen that before, but hey, it's fun. It's a nice short way of writing this. Then we produce the block for this slot with this parent. Then afterwards we say parent is ready, because now we produce the block, so we are the parent. Okay, and extra block production does what? Random fill bytes. Okay, so far so simple. I mean, it's pretty straightforward what it does. Let's start with the top maybe. Producing a block in slot 0. For 0 we don't need to check the parent. We voted on our own block with yes. 3 reconstructed the block. 3 also voted yes. 1 reconstructed the block, voted yes. 2 reconstructed the block, voted yes. And then 3 notarized fallback in slot 0. So this. It seems like that was not fast enough for the first one. But maybe that's just also for the first one. Weird implementation maybe. But then it's still 3 still says it fast finalized it. Fast finalized. All of them fast finalized them still. And then all of them slow finalized them. And then 0 produces block in slot 1. The others reconstruct it and vote yes on it. I wonder why they all still do notarized fallback. Oh, maybe that is notarized or notarized fallback. That would make sense. So they all say it got notarized. Or maybe, hold on. This is still a bit odd. I need to dig in here some more. So, right. So that means it's either a notar or a notar fallback. So all of the yes votes or fallback yes votes, so second round yes votes, so basically all of the yes votes go in here. And so that means there have already been enough yes votes. Those are the certificates that exist. Yes through fallback, skip, so a no, and fast final or just final. Wait, hold on, that still doesn't make sense. A fast finalization certificate is an aggregate of a strong quorum of notar votes. An aggregate of a quorum of finalization votes. Fast final, strong quorum of notar, final quorum of finalization. Does that make sense? Skip certificate is an aggregate of quorum skip or fallback votes. That would make sense. That's an aggregate of quorum notar or fallback votes. And that's notarization certificate is an aggregate of quorum notar votes. Yeah, that makes sense. It's a strong quorum of notar votes. Whatever. It's a bit confusing. Are we really talking about notar votes here? I mean, fast finalization can also have a fast skip. Does fast final really need to go through notar? Anyway, it's confusing. How did I get here? Basically, if we get a notarized or notarized fallback, waiting parent certificate remove. Notify parent. Basically, we're keeping track of the votes, notifying the others. I don't think I want to go like really deep into how it works with ascending between them. I think I just want to play around with it a bit more, because that's the more fun part anyway. You can go through the source code and try and understand it yourself. It's much easier to go through the source code yourself than me going through the source code and making it in a nice video, because it's just a lot and it's much easier to follow if you click through it yourself than if I edit and jump around. It just gets messy real quick. So I think it's just better if I play around with it and you watch me play around with it and then you dig through it yourself. How about that? And if you fast final, the highest finalized slot gets to the highest finalized slot. That's pretty simple. And same with the slow finalized. It's still interesting that I get the fast finalized and then the slow finalized for both of them, for all of them essentially. When do we produce that? In the voter loop. Let's check this. In the voting loop, if it's a retired slot, we ignore it. So if it's safe to notar, then that's basically the fallback. Then we broadcast our fallback vote. If it's safe to skip, then it's the skip fallback. Events from block store. Threads, we get blocks. Timers for a leader window starting at the given slot. So basically how we wait is just with timeouts. That's how Alpenglow does it. We basically just, wait until it's our time. Quick little hack in there. Try notar. Voted notar for slot. And here is where we actually vote for yes. Here we create the yes vote and then broadcast that to all of them with an all-to-all connection. That's how Alpenglow does it. And we try to finalize it. Okay. And same for try skip window. So for the slots per window, if it was inserted, indicated which slots were already voted for. So if we didn't vote for it, if we can insert, so if the insert gives us true, which means we didn't vote for that yet, then we didn't vote notar, so we vote skip. It's a simple implementation for that. And then we broadcast our skip vote. And if it was already inserted, then I could say here, I already voted yes for this. Let's do this just to prove that else already voted on slot S. Just so we see when it would do that. There we go. Let's see. Here, for instance. It never gets there. We never try skip window. Because we only call that. When do we call that? We broadcast our vote for a new notar fallback. And then we try and skip. Save to skip. Voted skip fallback. Fallback. Try skip window. Timeout crashed leader. Right. Only with the timeout we actually try skip window. And when do we get this vote event? Set timeouts for slot, spawn, asleep, delta, early timeout, 800 milliseconds. To use when we haven't seen any shred from a leader's block. Okay, so how about let's simulate that? How about let's crash one of our leaders? We have 4 of them anyway, right? We have 4 validators. Let's crash one of them. So non-crashed, it looks like this, right? It's always fast finalizing. Nothing particularly interesting here. But what if I tell one of them to not produce blocks? And in the simplest case, let's say validator number 1, not producing block in slot to simulate downtime or whatever. Let's say we are down, but we're not down, we're still voting, but we're not producing blocks. I just return here. Let's see how that would look. Oh, see, okay, hold on. The application panicked. Unwrap of a none. Yeah, probably because I'm trying to get a block hash of something. But that's fine because that's the number 1 that crashed, right? So basically then one validator is down and the others still continue. That basically just crashes my block production thread, I guess. The validator even still runs. It still runs, but it's giving me all of them here with the warn. They skip those 4 slots. All of them skip those 4 slots because they're like, no, you don't get anything here. So that's kind of working. I see 1, 2, and 3. Even the 1 is skipping the slot because it's not itself producing it. I vote skip on myself. Sure, that makes sense. It literally even voted skip on its own slot. Yeah, makes sense. If you don't produce it, you skip it. So 35 still got fast and then slow finalized. And then those are all skipped, the next 4. Till number 2 builds block in slot 35. Wait, block on ready parent. No, the ready parent is slot 35. And we are producing block 40 on top of 35. Yeah, that makes sense. That's fine. They basically just skipped that. I don't see a big problem with that. Let's see what happens because we're playing around with it. If all of them, maybe except for the first one, don't produce blocks. Do we get an issue here then? Because now 75% of block production is down, it should still be fine. They're all crashing now. It should still be fine because the voting, like rotor and voter, are still working. You know, basically we just skip everything except for 4 slots, and then we skip everything. Yeah, 4 slots, and then we skip the next 12, and then we produce 4, and then we skip the next 12. Then we produce 4, and then we skip the next 12. But it seems like it's still working, still running along. What if number 0 also doesn't? Let's say none of them produce blocks anymore. What happens then? With none of them producing blocks, this is just not gonna go so well, is it? Crash, crash, crash. Okay, and then we just voting to skip slots. But there was something with well, there was it. Well, hold on. I saw it. Recovering from a standstill at slot 0. Rebroadcasting 48 certificates. Yeah, so there is this recovery mechanism for so after 48 slots, roughly, it starts to recover. Let's watch it again. Basically, it will then just always increase the length of the timeout. There we just saw it. And there we saw it again. It was rebroadcasting votes at 96. And then again, wait, where did it go? Here at 144. They're all trying to recover from standstill, all 4 of them. And then again at 192. So pretty much every 20 seconds it looks like they're trying to recover. Does that match with the implementation? Recover from standstill, loop, delta standstill, 10 seconds. Timeout for standstill detection mechanism. So if we don't have any progress for 10 seconds, we try to recover from standstill. Because with slot times of 400 milliseconds, it should be then every 20 slots. But yeah, okay, whatever. Okay, how about that? They're all down for 69 slots. Let's see if they can recover then. Oh no, they won't be able to recover because I killed them. Build of our own block. Yeah, that's what's not working. Let's say unwrap or default, such that this doesn't die. We have a block hash of 0, but who cares? Not me. There we go. Now it's not dying, but it's giving me that note of we're not producing blocks to simulate downtime. And then there we go. After block 69, we're back to normal operations. There it recovered quite neatly. Once they all start producing blocks again, it's all fine. Okay, cool. What else? What else can we learn through here? Like, what's the learning opportunity? Let's go through the repo source code a little, just to understand the setup. So all to all, it's basically just communication stuff, I guess, like networking stuff, where we broadcast the messages, network send, network receive. You know, that's the lower level networking stuff. Consensus, there's the more interesting stuff with the block store. You know, that thing that stores the shreds and the slices and the blocks that it recovered, latest block hash. So yeah, when we get the shreds, we need to put them somewhere. We put them in the block store. And from the block store, where we will get events, reconstruct the block. There, then we send a voter event block to voter, and then in voter, in the loop, we get this from the pool. Down here, we get the events from the block store. First thread, block, a block was received, basically. So yeah, the block store is basically where we save the incoming stuff and also the stuff we build ourselves. So it's basically our storage of state. Certificates, there are the 5 certificates. Yes, yes with fallback, or yes through fallbacks. Skips, so basically the no, and then fast finalization and finalization. Epoch info is just storing, that's for our simulation basically. Those are the validators and my validator. That's all there is, really. And in this simulation, the leader is determined not through stake, but through, I mean, they're just equally given to the individual validators. So we have the leader ID is the window. So windows are always 4 slot parts. So every leader has a 4 slot window. And then I basically do a modulo of the validator length. So it's validator 0, then 1, then 2, then 3, then again 0, 1, 2, 3 for the case of 4 validators. That's how we assign who is the leader in this simple case. In reality, this is done through stake weighted. Yeah, that's the only interesting stuff in epoch info. Then the pool, that's also interesting, because here we add the certificates. This is the central consensus data structure. It holds votes and certificates for each slot. So for each slot, we have the votes and certificates in here, whereas the block store holds the incoming data, fundamental data structure for holding block data per slot. The block store stores the blocks, no shit, and the pool stores the votes, essentially. Votes and resulting certificates that we can build through the votes. That's stored in here then. Parent ready tracker as well. It does duplicate checking. And here we also do the updates if we get a certificate. For final, we basically just set the highest slot. For skip and for the notary votes, we always say the parent ready as a votary event, because we need to know when the parent is ready such that we can produce the block on top of that. Anything else interesting in here? Recovery from standstill is in here. A vote, 5 types. Yes, yes in fallback, no or no in fallback, and a finalization. And voter, this is probably the most interesting part. Here's where we actually handle those events then. Voting loop. Yeah, and then crypto, yeah, that's just stuff that we use, I guess. Merkle tree signatures, not too interesting, I would say. We didn't look at that really yet. The rotor sampling strategy picks validators directly proportional to their stake. Uniform sampler, basic sampler, all validators are equal. So here we have different samplers. King acceptance sampler, hybrid sampler. So I see different turbine sampler, distribution in turbine for rotor. So here there's different sampling strategies, and then rotor itself. That's basically where the shredding comes in. Then we send, rotor is responsible for, you know, sending out, when we produce the block, we send it to a fixed number of validators in shreds. That's essentially what's happening here. Network send to this one, send as leader. Then the others broadcast it. I guess that's how it works, right? The leader sends it to K validators, and then those K validators broadcast it to all of the validators. Why doesn't the leader broadcast it to all of the validators in the first place? Probably efficiency, like because that's a lot and the leader has better things to do than, you know, networking when it's their time to produce a block. So they just send shreds to a few validators, and then those few validators who are not currently busy producing blocks, they transmit it to the rest of the cluster. I think that's the idea behind it. Basically, they just relay. Nothing if we're not on the relay, and if we are, then we broadcast to all of the validators, unless it's the leader or another relay. Okay, no, it's off that particular shred. So except for ourselves, essentially, we would guess that our ID is relay. So, you know, unless it's us or the leader, we send it to them. Yeah, that makes sense. And that's essentially rotor. And there can be a sampling strategy for how to pick where we send, like where we send the shreds to, I guess. To figure out who's the relay, the sampler is used as well. That makes sense. Okay, that's rotor. Pretty simple if you read through it. Like, it's not complicated. It's not, this whole algorithm is not complicated. That the reference implementation just has a few files with a few lines of code. It's quite trivial, as this file makes you believe. And I don't know why we have turbine here. Maybe for comparison, because we don't really need turbine for Alpenglow, and we also don't really need Merkle trees. That, like, turbine needs that. But yeah, the whole networking stuff, I don't think I want to look into that, because, you know, I mean, UDP and stuff, you know how that works. And if you don't, it doesn't matter. That's the low level, you know, working with sockets, working with IP, you know, whatever. That's not like Alpenglow specific, so I'm not even going to look into that. Orchestrator, the hell is that? AWS. Yeah, the really interesting part is in consensus. So yeah, I think I'm good with that. We played around with it a bit. I gave you a broad overview of where you can find stuff. Look at it yourself, play around with it yourself, and it keeps crashing. There we go, and then it recovers. Nice. So yeah, source code for Alpenglow is released. It's a reference implementation. It's one possible implementation that's basically just for simulation and proof of concept kind of. But it exists. If you want to understand or more deeply understand how Alpenglow works and you're a dev, like you're a coder, you can read and understand source code, then I would recommend that you look at that. Just for fun, just to learn more about the protocol, because I think that that's coming, and that is one of the things that I'm most excited about in terms of what's ahead for Solana. And as mentioned before, I will make more videos about it once we have an actual, release candidate, like a proper implementation by one of the Solana validator clients. Basically an integration of that into the validator, which is also being worked on or already exists, but is more complicated to look at because, it has all the validator code as well that I never looked into yet. So it's just too much. But this little repo, I can recommend that you check it out. It's pretty cool. Pretty cool playing around with it. It's just one of the things that you can do. You don't need to, of course, but you can. And you can also watch those videos, give this one a like, subscribe if you haven't done that already. You can't do that if you have already done that, so congratulations on not being able to do that. And then I will see you in the next video. If you have interesting wrappers for me to look at, let me know.